Last but not least, I would like to talk about continuous functions, which just means that if the inputs are close together, then the outputs are close together as well. So let's say here if you have x naught and f of x naught, all this means is that if x is close to x naught, then f of x is close to f of x naught. And now it turns out there are two different definitions of continuity that are actually equivalent. One is with sequences. So f is continuous at x naught if, whenever xn converges to x naught, then f of xn converges to f of x naught. In other words, literally, if the input xn is close to x naught, so xn converges to x naught, then f of xn converges to f of x naught. Okay? So that's one thing, the intuitive definition. The other one is the infamous epsilon delta definition, which is more powerful in my opinion. So f is continuous at x naught if for all epsilon there is delta such that for all x, if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon. So what does that mean? It means the following. So again, suppose you have f, this is maybe x naught with f of x naught. What this means is, no matter how small the error epsilon, and remember for an error we then get this good region. So no matter how small epsilon, there is some threshold delta such that if the input is delta close to x naught, so this is delta, so if x is within this red region of radius delta, then f of x is guaranteed to be in the good region of radius epsilon. So in other words, no matter how small the error, there is a tolerance such that if x is close enough to x naught, then f of x is close enough to f of x naught, which is precisely what we want in continuity. Now, the nice thing is, a lot of functions are continuous. So for instance, the function x squared is continuous, but also e to the x, sine of x, etc., etc. They're all continuous. And not only that, we have nice laws such that if f and g are continuous, then f plus g is continuous, f times g is continuous, even g composed with f. So do f first and then do g. And also if f is invertible, then f and continuous, then f inverse is continuous. For instance, arctangent is continuous wherever it's defined. And not only that, continuous functions have really nice properties. And in fact, let me talk about some of the properties. First of all, if f, let's say from a compact set to R, is continuous, then f is bounded. Meaning it doesn't suddenly blow up to infinity. So if you have, again, it's a function defined on a compact set, it can't just look like that, where it blows up. It has to be nice and bounded. So maybe something like that. Not only that, there is the extreme value theorem, which just says that if f from a to b is continuous, so a function from a compact set to R is continuous, then f has a maximum and a minimum. max and min. So the maximum and the minimum of f are attained. For instance, here's the maximum of f, which is f of something, and here's the minimum of f, which is f of something else. Okay, and so the extreme value theorem is true, but also the intermediate value theorem. So that was the EVT, now the IVT. And it just says, has nothing to do with compactness, but more with connectedness. It says that if a function from a to b to r is continuous, then it attains all the values between f of a and f of b. And let me illustrate. So suppose you have a function here, f from a to b, and this is f of a, and this is f of b. Then for any c between f of a and f of b, the value is attained. So in other words, there is some x between a and b such that f of x equals c. So then for every c between f of a and f of b, we get that there is x in AB. X in AB with f of x equals c. And from this we get nice identities like, nice applications like fixed points, or we can construct square roots. Alright, and related to continuities, there's a stronger notion called uniform continuity, which just means that the delta doesn't depend on where you're at. So definition, f is uniformly continuous on a set S if for all epsilon there is delta such that for all x, y in S, x minus y is less than delta implies f of x minus f of y is less than epsilon. And again, the crucial difference is in continuity, delta can depend on x naught, but for uniform continuity, it doesn't. In other words, no matter how small the epsilon is, there is always some universal threshold such that no matter where we are, so there's a delta, such that no matter where x and y are, as long as they're delta close, we're guaranteed that f of x minus f of y will be epsilon close. So the outputs are guaranteed to be in a region of size epsilon. Now, of course, uniform continuity is stronger than continuity, but also we have the following nice three facts. So first of all, a function f on a compact set that's continuous implies that f is uniformly continuous on this. And not only that, uniformly continuous functions behave very nicely with Cauchy sequences. So if Sn is Cauchy and f is uniformly continuous, then f of Sn is Cauchy. And they also behave very nicely with continuous extensions. So f from, let's say, an open interval AB to R is uniformly continuous if and only if f has a continuous extension, f squiggled from AB to R. So in other words, if and only if we can extend f to a continuous function on the whole interval. So if and only if we can define, if you want, f squiggled of A and f squiggled of B to have the whole interval. And for this reason, x sine of 1 over x is uniformly continuous on 0, comma 1, because this function, we can just extend it to be 0 at 0, but sine of 1 over x is not uniformly continuous on 0, comma 1, because this function, we cannot extend it to be anything at 0 with being continuous. Thank you.